In this NESI hardware tutorial, we will be going over the types of sensors and hardware you will need in order to carry out the Clear Springs Hunch program project. The video will be divided into two sections, which are theory and application. The 3 steps of problem solving will allow you to tackle any future projects given other than the specific example given in this video. The divisions of problem solving will allow for an easier and clear overview of your project in order to have an easier time working on the project itself.
In order to solve a problem, we must find what the problem itself is. Make sure you fully understand the requirements of what you're trying to solve so that you stay on topic and don't stray off in another direction with unnecessary work. You do not want to go into detail about the problem itself because identifying the parameters is a whole different step.
Step number 2 is to identify the parameters. So what exactly do we need in order to carry out the solution for the problem? This may seem very vague right now, but we'll cover in more detail when we go through the example project.
Step 3 is identifying the hardware required to satisfy the parameters. We identify the parameters in a separate step so that we may easily satisfy them with the required hardware. Identifying the hardware is actually a 2-part step in itself due to the fact that we must first find what we actually need and also know why we need the equipment that we have chosen.
Now, using what we just learned, we're going to go ahead and apply those 3 steps to an actual project. So identifying the problem. We want to design a plant growth chamber that will grow beans supported by a given artificial biome in order to reduce the need for food resupply in space, especially for long-duration missions for NASA. In step number 2, we needed to identify the parameters of our experiment. So our physical requirements are we need to be able to fit this experiment within a small NanoRacks box. Measurements we needed to take are hydration and CO2 levels. We need to be able to take pictures every 4 hours. And also to control water distribution so we can continue to allow the plant to grow. We also need to simulate some daylight using LED lights. And then, of course, taking pictures and recording data, we need to be able to store that on some data stick. We also need to be able to access for user interface to test a program without having to dissect the NanoRacks boxes, so it's easily accessible. We are now on the 3rd and final step. We will now be going into description and uses for each hardware device chosen, as well as how to install them on the NESI board. This is the moisture sensor. It's going to measure the resistivity between the rock wool to see if it has been dried out or not to send data to water it. There are 4 places to connect the moisture sensor. You have one in all 4 corners. Here, these 2 pins, B and A, on all 4 corners. So for this example, we're only going to be connecting one resistive sensor. So you're going to choose one of the 4 corners, and then you're going to grab a header pin, like such, and once you solder it in, now you're ready to connect your resistive sensor. Now all you need to do is jump each one wire to the other. So the final connection should look like this. We want to be able to take pictures of our project every 4 hours, so we're going to be using a camera that communicates over UART to plug into the NESI board.
The camera simply plugs into the port labeled camera. It will be hovering over the microcontroller like so when you are finished. Based on our reading from the moisture sensor, we'll be needing to control the water flow within our project. In order to do this, we'll be using the 0.062 MinStack MIV solenoid microvalve.
The solenoid valve is a lot like the moisture sensors. There's only 2 places where you can plug a solenoid valve in. Right here labeled power driver A, and right here labeled power driver B. So like before, put in your header pin, solder it down, and then connect your 2 wires across. It should look just like this. The NESI board is optimized for the MG811 CO2 sensor. This sensor will measure how much CO2 is in the air and will be able to determine how well the plant is growing.
The gas sensor will simply be placed where it is labeled gas sensor. The orientation of the gas sensor does not matter, so you can just slide it in like so.
Make sure to solder the leads at the end.
We're using the LED to simulate daylight. It is crucial to find the negative side of the LED, so seeing on the picture to the right, the negative part of the LED is the largest plate when you look inside of the LED, as seen there. The NESI board has 8 LED ports. You can see all 8 of them right here. Now if you flip the board on the other side, you can see that they're all labeled. So you have LED 1, 2, and then all the way around. Now it's important to know which side of the LED is negative, because if you look closely on the board, you'll see this thick white line right there, which symbolizes that's where the negative lead of the LED goes into. So I'm going to put the negative lead in right here, just like that. Now if you put it in backwards, the LED will not turn on and most likely burn up. So make sure to get it right. And then whenever you're done, solder it on the back and clip off the leads.
Our project will require us to store our data, so we'll be using a micro SD card. We will need at least 1 GB of memory within our project.
The SD card simply slides into its slot. When using one, just make sure you plug it into the primary SD slot.
The NESI board already has an onboard push button, but if you cannot easily access it, then this is how you install an external button. The external button is just like the moisture sensor and the solenoid valve. Right here is where you're going to put your jumper, and then you're going to be able to connect your 2 wires from your external button across them.
Now that we've finished everything with the hardware, we can move on to the software.